Let's look at some of the nomenclature associated with carbohydrates. So right off the bat, let's sort of define carbohydrates. Carbohydrates, they got a lot of names. Sometimes they're called sugar molecules. Another one that you see maybe not so often is a saccharide. But it's just many ways of saying the same thing, which is one of these compounds, carbo, which means carbon, hydrate, which means H2O. So it's a biomolecule, and like I said, it consists of carbon, hydrogen, and oxygen, and it usually has this ratio of 2 to 1. So let's take, for example, glucose, C6H12O6. You can see it has this kind of formula, CnH2O, and in this case, N equals 6. So it's these kind of long chains of carbon atoms, and it's got alcohols dangling off the carbons, or in some cases, aldehydes and ketones, and we'll talk all about that. Now, when we look at how we classify carbohydrates, all right, the three main ways that we classify just the chain is one by the chain length, so how many carbons are in the carbohydrate. The rule for how we do this is similar to the prefixes that we use in IUPAC naming, which is to say if there's 3 carbons, it's a tri-carbohydrate. If it's 4, it's a tetra or tetra or whatever. 5 is pent, 6 is hex, and hept is 7. And in all cases, it ends in ose. So it could be a triose if it had 3, a tetros if it had 4, pentose, hexose, heptose. The second thing we want to look at is it an aldose or a ketose? Sometimes they're called aldulose and ketulose. They add a UL in there. I mean, this is classic chemistry stuff. They just throw in letters. But in general, aldose and ketose, these are the ones that you need to be able to identify to name these carbohydrates. And it's classified based on if it has a presence of an aldehyde, it's going to be an aldose, right? The name ald kind of is consistent there. And if it has a ketone, it's going to be a ketose. And the last thing, and it's probably the most tricky for classifying carbohydrates, is whether it's a D or L carbohydrate. If you have a D and L carbohydrate and it's the same one, D glucose and L glucose, this is two ways of saying, like, these are the enantiomers of glucose. There's D glucose and L glucose, and they're the same. They're just related by that mirror plane. Very similar to R and S, except all of the chiral centers are opposite in D and L versions of the same sugar. But when we want to just classify a carbohydrate as D or L, sometimes we're just asked to do that, not really know its name. We just want to say, is it D or L? We do it in 3 steps. We look, usually it's done on a Fisher projection. Step 0 might be draw the Fisher projection of the compound. But once you have your Fisher projection, you want to draw it so that the highest oxidation state carbon is at the top. This might involve rotating your Fisher projection 180 degrees so that the highest oxidation state carbon is at the top. And then that's how you start your counting. So usually it'll be an aldehyde that's at the top or a ketone, and I'll highlight those examples as we go through them in the example coming up. Okay, so we're going to put the highest oxidation state carbon at the top. Then we're going to go all the way down to the bottom of our chain where we will find a CH2OH group. And we want to make sure that that CH2OH group is on the bottom. That is to say, we've got the bottom of our carbohydrate chain, and so we have our CH2OH in the bottom position of that line. So it's all the way down at the bottom. And then what we do is we assign our D or L based on the location of the OH. So if the OH is to the right, in this case, that would be a D sugar. And I'll just draw another one in green. We have our CH2OH. And if the next OH up is on the left, it's a L sugar. So the way to remember this is just remember L means left and D is the other one, which is right. So that's how I've always done it. Okay, so L is left and D is right. So let's try naming these following carbohydrates. We got 5 carbohydrates here. You can pause the video here if you think you want to give it a shot, or you can pause the video after I do the first one and then try the next 4, or you can just wait and we'll just do it all together. Okay, so let's start with number 1. We can count the number of atoms that are in it, but it might be most useful to make sure that we have the highest oxidation state group at the top before we number any atoms. In this case, we have our C-double bond O closest to the top of our drawing, so that's good. And then we start numbering the atoms based on that position. And this numbering is also consistent with the carbon the numbering for the carbon atoms within our sugar molecule. So if we say carbon 1 or carbon 4, it's going to be consistent with the numbers I'm about to draw. So number 1's at the top, 2, 3, 4, 5, 6, 7. So we have 7 carbon atoms. The numbering is as you follow. So if someone's like, okay, well, we're doing a bond with the alcohol on carbon 4, that refers to the alcohol that's on carbon 4, the one we put a 4 on. So chain length, this is 7, which is hept. So this is a heptose. Is it an aldose or a ketose? Well, it has a ketone, so it would be a ketose. Oops, no, just a ketose, not a ketose. And is it a D or L sugar? Well, we make sure that our CH2OH is on the bottom, and it is. And we can see that the OH is in fact on the right, which makes this a D sugar. Pretty straightforward. You know, now you can pause it and try your hand at the next few if you'd like. All right, number 2. Again, our aldehyde, highest oxidation state's at the top. We're going to number all of our atoms. These are our positions. If we were to talk about the different atoms, we have tetrose. There's 4 of them, tetrose. We have an aldehyde, so it's an aldose. And if we look at our CH2OH, the OH is now on the left-hand side, so this is an L sugar. All right, next one. We have a ketone in it, but it's closest to the top. If we tried to rotate this molecule 180 degrees, for example, the ketone would be 1 step down, and so it would be technically in a lower position, a lower numbered carbon. So we now number everything. All right, we have 6 carbons, so this is a hexose. We have that ketone, so it's a ketose. And if we look at our CH2OH, we can see that this is in fact an L sugar. All right, moving along, aldehyde. Again, closest to the top, we have 1, 2, 3, 4, 5 carbon atoms, so that's a pentose. Aldehyde makes it an aldose, and our OH is on the right hand side, so we have a D sugar. Last one, aldehyde, again on the top. We'll number our carbons in green to be consistent. 1, 2, 3. That's a triose. It's an aldose, and it's a D as well. Again, D because it's on the right. Okay, so those are those 3 main classifications. But it can become tricky when we actually start looking at the more cyclic forms of sugars. We don't always get them as these acyclic Fischer projections. We often see them as acyclic. We often see them as cyclic hemiketals or hemiacetals. Remember, when we have these ketones or aldehydes with all these alcohols around, the cyclic forms of these hemiacetals are more stable than the ring open form ketone or aldehyde. So we actually get preferential formation for our cyclic hemiketal or hemiacetal form. So we'll often see carbohydrates drawn as either 6-membered or 5-member rings. And this introduces kind of a key term. A 6-membered ring is referred to as a pyranose ring, and a 5-membered ring is referred to as a furanose ring. And the main thing to remember is the 5 and furanose, and then just remember that pyranose is the other one, and it's either going to be 6 or 5 because those are the 2 thermodynamically favored ring sizes, and the F ring, furanose, refers to the 5-membered ring. Okay, so let's try naming these carbohydrates, these sugar molecules, by chain length, whether they're aldose or ketoses, and whether they're a pyranose or a furanose. So we'll start with just the pyranose and furanose. I'll do that in green. Okay, so we're looking at the number of atoms that are in the ring. In the case of number 1, we have 6 atoms in the ring, so this would be a pyranose. Number 2, we've got 5, so this is a furanose. And number 3, we've got 5 as well, so this is a furanose. Easy so far. Okay, so here's where it gets a little bit trickier. Now we want to identify whether it's an aldose or a ketose. So for aldose and ketose, and I'll try and do this in red, the important thing is to find the anomeric carbon. And we're going to talk a little bit more about anomeric carbons in a second, but the anomeric carbon is going to be the hemiacetal or acetal or ketal or whatever, but the same trick applies. We're looking for the carbon that has 2 CO single bonds. That's the first step to identify whether it's an aldose or a ketose. So if you want to pause the video here, you can try and find the aldose or the anomeric carbon in these 3 examples. Okay, so again, we're looking for carbons that have 2 CO single bonds. So I'm going to dot all the anomeric carbons, and then let's do it in blue. I'm going to highlight the CO single bonds. So you can see that carbon that I've dotted in red in all cases has 2 CO single bonds. And in all cases, they're hemiacetals or ketals. Now when we start our naming, what we need to essentially do is imagine that we're breaking the CO bond that's in the ring. And in the case of an aldose, we're going to have, and I'm just going to kind of draw a shortened form of this ring to the side. What we're doing is imagining, and there's just a bunch of stuff dangling off there, that this oxygen in green is opening up to reveal this alcohol and reform whether it's an aldehyde or a ketone. Now, if it's a acetal or a hemiacetal, so in this case on the red one, what we don't see is this hydrogen coming off. If it's a hemiacetal, that means it must come from an aldose. So this is, number 1 is an aldose. Because again, once we open up that ring, we're going to form either an aldehyde or a ketone. And in the second case, if we were to open up, again cleaving that CO bond in the ring, and I'll kind of do my best to draw it off to the side here. And again, I'll make that alcohol that's in the ring green. What we end up forming is a ketone, because now we have that CH3 group bound to the anomeric carbon. So that would have come from a ketone, which makes this a ketose. In our last case, we have a proton there in the number 3 furanose, so this would be an aldose as well. Okay, so how do we figure out the chain length? Now we're just concerned with carbon atoms that are in the ring. So I'm going to try and we'll do it with blue. Hopefully it doesn't get too confusing. We can start counting number 1 at the aldehyde. There's not going to be anything attached to it, nothing above it. So we start our counting at the anomeric carbon. 1, 2, 3, 4, 5, and then this last carbon, 6, is is included as well, and we don't concern ourselves with any of the groups that are kind of bound to it. All of those methyl groups, or OCH3s, aren't in the main carbon chain. So we in fact just have 6 carbon atoms within this group, or this carbohydrate. So this would be a hexose. It's a hexose, pyranose, aldose, right? Okay, what about number 2? Well, this one's a little bit trickier because it's a ketose. And if you remember, with all these carbon chains, we start the counting at the very top of our carbon chain. So we actually start counting at the CH3 that's bound to our anomeric carbon. And if that was like an ethyl group or it had more carbon chains on it, we would start counting at the end of that chain. Again, just trying to have our ketone at the lowest number we can have it, whether we count from the bottom or the top. But we have to include that carbon in our carbon chain counting. So we have 1, 2, 3, 4, 5, 6, 7. Again, all of these carbons in that chain I just highlighted in blue, although maybe I'll do it in red and try and make it a little bit more clear. But all of these carbons are included in our chain. And so that means that we have 7, which means we have a heptose. So this is a heptose. And in our last case, and again, just to sort of remind you, all that stuff that's dangling off the sides, we don't care about. It's only the things that are in the main chain that are carbon-carbon bonds. All right, last one. Again, we're starting at the anomeric carbon. Since it's an aldose, we're going to have that anomeric carbon be number 1. And now we're counting everything in the main chain, all these carbon-carbon bonds, starting at 1, 2, 3, 4, 5. So that's a pentose. And then those numbers that we use there also refer to the positions of the things bound to them. So we can see that we have a ring that's being formed from the alcohol on carbon 4 with the aldehyde on carbon 1. All right, another important thing to be aware of is whether it's an alpha versus beta anomeric center. And we introduced this idea of the anomeric center. It's the position where we have this hemiacetal or acetal or ketal. And depending on the orientation of that OH group or O whatever group, you can have either an alpha or beta anomer. So like I said, it can exist in 2 different forms. We can have alpha or beta. So the naming is related to the orientation of the oxygen off the ring, which I guess I'll do in green to make that kind of clear, and the CH2OH group, which I'll do in red. So in these 2 examples below, our CH2OH group, I'm just going to highlight in red, and our OH is in green. Okay, so the way that we assign the name, alpha means opposite. The orientation of the CH2OH and the OH is opposite. I choose to remember that because both those words start with vowels. Opposite and alpha start with vowels. That's just me. And beta is the same. There's no easy way. I don't know why I circled the B and the S. There's no really clear way to remember that. Maybe you have a good one, but I just do alpha, opposite, and then the other one, beta, is the same. So we have, in the first case, an alpha isomer. We can see the CH2OH is up in our ring, and our OH is down. So these 2 are opposite in terms of their orientation, which makes this the alpha isomer. Alternatively, in the second case, we have a CH2OH which is up, and our OH which is up. That means they're the same. Again, we're just looking at the orientation of the OH on the green dotted carbon, which is our anomeric carbon. Now, what's the relationship between these 2 compounds? Well, if they differ just in the orientation of the OH group, but everything else on them, so all the other OHs are the same. The orientation of those is the same. Remember, the orientation of that OH group is just based on the opening and closing of our cyclic sugar structure, from a hemiacetal to an aldehyde back to a hemiacetal. So they actually aren't different structurally. They're just different tautomers of each other, but they have been assigned a special name because they differ in the orientation at the anomeric carbon. We call them anomers. And different anomers are going to have different optical activity, but they structurally are the same, and they have the same sort of features. And you can interconvert between two anomers in a relatively straightforward fashion. The last thing to think about in nomenclature is glycosidic bonds. So if you have a ketal or an acetal instead of a hemiacetal or a hemiketal, you have created a glycosidic bond. This is just a special bond that changes the ability of the carbohydrate to interconvert from its cyclic and acyclic forms. So here we have a glycosidic bond between just oxygen and this ethyl group. And even though it's a small ethyl group, we still call it a glycosidic bond because it's at our anomeric carbon, which again is the carbon with the two CO bonds, and we just have some R group bound to it. But more traditionally, you'll have a glycosidic bond, like in the second example, we identify our anomeric carbon, and it's got a linkage between that OH and another sugar molecule. So this is kind of where the glycosidic bond term comes from. Now we can assign glycosidic bonds the same way we assign anomeric carbons. So whether they're alpha or they're beta, we do the same thing. So again, I'll do in red my CH2OH, and in green I'm going to do my linkage. And in the first case, CH2OH is up. My OR, R just being some group, is down. They're opposite. So we would say this is an alpha glycosidic bond. Again, that OH or OR group is alpha to the CH2OH. In the second case, we have CH2OH up. The OR group is up. That's the same. So we call that a beta glycosidic bond.